Calculating double integrals can get a little annoying because it's two integral problems and you have to sort of work out one integral problem completely before you can even start the other integral problem, which is a bit of a pain. But if we think about it carefully, there's a slick trick that we can do for many integrals, not all double integrals, but many double integrals. And so let's see how this works out. So let's calculate the integral over this rectangle of the function x times y cubed over x squared plus 1 dA. Remember, to actually evaluate a double integral, we write it as an iterated integral. And in principle, we could put the variables in either order. So let's put the x integral on the outside, I guess. So integral from 0 to 1, and then integral from 0 to 2 in the y direction, x y cubed over x squared plus 1 dy dx. Okay, and then the way that we have done this in the past is just to work out the inside integral completely, and then when we are done, then work out the outside integral, which is a bit annoying. But one thing we could do with this is we could rewrite this integrand as x over x squared plus 1 times y cubed dy dx. But then this function right here, x over x squared plus 1, it doesn't depend on y's, right? No y's in here. So as far as this inside integral is concerned, this x over x squared plus 1 appears to be a constant, right? Since it doesn't have any y's in it, and this is a y integral. So since this expression doesn't depend on y, it appears to be a constant multiple for the inside integral, so we can slide it outside of the inside integral. So that gives us the integral from 0 to 1 of x over x squared plus 1, integral from 0 to 2, y cubed times dy dx. Okay. But hold on a second. Now the inside integral, this entire inside integral, doesn't have any x's in it. So as far as the outside x integral is concerned, this inside integral appears to be just some constant, right? If you worked out what this inside integral was, it'll just be a number. So now this inside integral appears to be a constant multiple, and so we can slide it outside of the outside integral. And the upshot of all of this is that, when we write out what we get, integral from 0 to 2 y cubed dy times the integral from 0 to 1 of x over x squared plus 1 dx. The upshot of this whole process that we went through is that the integral that previously was an iterated double integral up here, we have split it apart, so now it is the product of two single variable integrals. Right? And this is pretty handy because now we can do these two single variable integrals simultaneously. So this first one, the y integral, I guess is going to be 1 over 4 y to the 4th from 0 to 2 times, and then the x integral I think is going to be, looks like it's going to be 1/2 natural log x squared plus 1, I think. Yes, from 0 to 1. Okay, and then we can continue to evaluate these simultaneously. So 1 over 4 times, and then plug in our bounds. 2 to the 4th is 16 minus 0 to the 4th is 0 times 1/2 times, and then plug in our bounds, natural log of 2 minus natural log of 1. Natural log of 1 is 0. Okay, these constants we can pull to the front, so 1 over 8 times 16 times natural log 2. So 16 over 8 is 2, so 2 natural log 2. Okay, so this is much nicer because we got to do all of our work for the y integral here at the same time as we did our work for the x integral, right? So it's just a little nicer, a little more efficient. So let's think, that's such a nice trick, and this happens pretty frequently. So let's take a second to look at what exactly about this example is what made this work, right? what made this work is that at the very beginning, we were able to take this y cubed and kind of move it out of the way so that we had a function of x times a function of y. And that's the key thing. So the reason this trick worked is because our integrand is a function of x multiplied by a function of y. Okay. Something that isn't so obvious about why this worked, let me back up a slide. Something that isn't so obvious about why this worked is that right here, when we slid the y integral outside of the x integral, x didn't show up anywhere in this integral. And although we haven't seen this yet, one place x can show up is in the bounds. Okay, so we'll study that later, but the fact that the bounds themselves were constants was also a key ingredient of this trick. So the two ingredients we need for this trick is that your integrand function has to be a function of x multiplied by a function of y, and also the bounds have to be all constants. Okay. So just one more example of using this trick. Let's evaluate the integral of x times y times cosine y dA on this rectangle. Okay. This is x times y cosine y, and of course all our bounds are constants. So right away we realize, oh hey, we can split this up into an x integral times a y integral. So the x integral is from 1 to, well, let's write out the integral completely first. So the iterated integral is the integral from 1 to 5, integral from 0 to pi of x, y, cosine y, dy dx. Okay, this is a function of x. Our integrand is a function of x times a function of y. All our bounds are constants, so we can split this up. The x integral is from 1 to 5, x dx. The y integral is from 0 to pi, y cosine y dy. And now we can do these integrals simultaneously. So let's see if I can fit this all in the space that I have left. The x integral I can definitely fit. So that's 1/2 x squared from 1 to 5. The y integral, well, we're going to have to use integration by parts, right? So the y here, that's going to be u. Cosine y dy, that's going to be dv. So to get u times v, that's going to be y times sine y evaluated from 0 to pi minus the integral from 0 to pi of v du, so that's going to be sine y dy. Okay, so this x integral is going to be 1/2. Let's see, 5 squared is 25, minus 1 squared is 1. And then the y integral, let's see, when we plug pi into this, we get 0, because sine of pi is 0. When we plug 0 into this, we get 0. So 0 minus, and now this final definite integral of sine is negative cosine, so that extra negative turns this minus to a plus. Cosine of y from 0 to pi. So this is going to be, let's see, 25 minus 1 is 24, over 2 is 12 times, and then when we plug in our bounds, I think we're going to get minus 2. So altogether we get minus 24. All right, pretty slick. It's nice to be able to split up an integral like this, right? So again, the ingredients that made this work is our integrand was a product of a function of x and a function of y, and our bounds were all constants. Okay. Do be careful with this trick. So remember, it has to be a product, right? So let's evaluate this integral. Writing out this double integral as an iterated integral, just for variety this time, let's put the y on the outside. So integral from 1 to 4, integral from 0 to 2, x plus y dx dy. So if you're sort of uncautious, it's tempting to say, okay, well, let's do the splitting up trick. So integral from 1 to 4 of y dy, and then there's a plus, so maybe we put a plus here, integral from 0 to 2 of x dx. Well, no, this is plus, not times. There's nothing that we figured out that said that you can split up your integral into a y integral plus an x integral like this. In fact, we know that we can't. One of the properties that we looked at earlier is if you have an integrand that is a sum, right, the integral of a sum is the sum of the integral of your two functions, but these are still double integrals over your region, right? So if we're going to evaluate this integral, we could split this up into the double integral from 1 to 4 and 0 to 2 of x dx dy plus the double integral from 1 to 4 and 0 to 2 of y dx dy. Right? But these two integrals are still double integrals. These are not single variable integrals. Okay. And then we could evaluate these separately. In fact, now this integrand is a function of x times a function of y. So if we wanted to, we could split these up. Integral from 1 to 4, that's the y integral. So there's a hidden times 1 in here, and so that could be our function of y. So 1 times dy times the integral from 0 to 2. That's our x integral, so x dx plus, and then, the same kind of thing over here. Integral from 1 to 4. This time our function of y is y dy, and integral from 0 to 2. And our function of x this time is 1, so 1 dx. And then we could compute all of these. Right? So for this particular integral, I don't know that it's particularly profitable or time-saving to think about splitting it up this way. This particular example is straightforward enough just to do the iterated integral directly. But if you do want to split it up, be careful about how you split it up. Right? This trick of separating integrals into two single variable integrals, it works when we have multiplication, not addition. Right? Okay, so just to finish this off, let's see, the integral from 1 to 4 of 1, that's going to be 3 because 4 minus 1 is 3, times, and then the integral of x, so that's going to be 1/2 x squared from 0 to 2, plus integral of y is 1/2 y squared, that's from 1 to 4, and then the integral of 1 from 0 to 2 is going to be 2. Okay, so this is 3/2 times, and now plug in our bounds. 2 squared is 4, 0 squared is 0, plus 1/2, times 2, so that cancels the 1/2. And then 4 squared is 16, minus 1 squared is 1. So over here we have 3 times 4 over 2, so 3 times 2 is 6, plus 15. So 21.